So it should be coming up here in a short bit, hopefully, and we'll see. All right, so yesterday we looked at variables. We were asking what the IV and DV are for this example with Susie. Whoops, I need to switch my screen. There we go. We'll get to the homework later. There we go. Okay. This is what we were looking at. All right, and so we left with the question or ask to check in on Kevin's idea here. He wants to know if changing the amount of water will delay the leaves of a tree from dropping. And the ask from me to you was in your note set, sketch in what you think the independent variable is in this experiment and what is the dependent variable in this experiment. And we also need to be specific about what either is. Now we're good? Good. Great. Sorry. Yeah, you're right. It hasn't been 24 hours yet. But we'll flip the lights around a little bit here. Okay, so what did we come up with? What is the independent variable in his experiment? Yes? Isaac.
Yeah.
Yes.
The amount of water that he's adding.
Yeah, he's changing the amount of water that he's going to give these trees. And okay, so what's the dependent variable? Noah's in the front. You must be Doug.
No, I think I found the
Help me out.
YouTube problem though.
Okay, what's the problem?
It's in the top right. There's a button that says sign in, but when you click on it, you can't sign in with the school email. I think that's why it's not letting us on because we're not signed into YouTube with the school email.
They restricted YouTube so it doesn't show inappropriate stuff.
Right. We know that. Well, we know that. I mean, that's what we were trying to fix. I will pass that along to her and see if maybe there's some way that they can.
No, only sign into a different computer.
Okay. So you cannot sign into YouTube. Period.
I did.
All right.
But that's what it tells you to do when it doesn't show the video.
Okay. I will pass that on. Maybe that'll help her track down the problem. How can we just get rid of the filter? No, we can't do that. Okay. Yeah. Okay. So the dependent variable.
How many leaves drop off? How many leaves fall off the trees?
Okay. How many leaves will fall off the tree, and how will specifically how might we measure that? Like if you want to know how many leaves fall off the tree, what's probably the easiest thing that you could do?
Look at the ground.
And
Look at the tree. Count them.
yeah, we could count every single darn leaf that falls off the tree. And we could do that. What might be some problems obtaining that measurement? Yeah, go ahead.
It would be dead, and then all the leaves from other trees just blow in, and that's the point of it.
That's true. We might have trees of the same species right near one another, and you're going to get leaves from one tree mixed up with leaves from another one. Sure. What else? Or is there any way we can? What are some ways that we can fix that? Is there any way that we can still not kill the tree but still collect the leaves it drops? Yes, Doug. Help me. What is it? Elijah. Okay. Elijah. Also, AKA Doug. Idea.
If it was wanted to completely isolate, you could throw the tree in a room or something, or have a fence around it, so that.
Okay, so we can plant the tree in 30 years run our experiment. Well, yeah, we could construct some sort of apparatus around it. All right, but what if we have a rather large tree? What if it's like large redwoods, out in Yosemite or whatever? I mean, probably not feasible to build something around it. Yes.
Put a net around it.
We could put a net around it, sure, right? And then we can very careful. But now, what might be a problem with adding a net to it, though? She's not going to want to be a tree all out long, will she? A net. Yeah, she wouldn't like that. No, I'm joking. No, what might be a problem? Well, animals in the tree, okay, that'd be a problem. What might be a problem with putting a net around or on the tree?
It'd be a really big net.
It'd be a really big net, and if it was touching the tree at all, it might pull leaves off or something when we put the net on. So that's going to affect our data. Yes, ma'am.
A way you could do it is you could count the number and then use estimation to like measure the area, measure a certain area around the tree so you know how many square feet. And so if so many leaves fall here, approximately blank leaves fell off the tree, depending on the area that's marked out.
Yeah, that might be a method that would be feasible. And we would definitely want to run our experiment several times to try to average our data collected. But and you're right with all these other ideas, like, well, we might have like winds that blow leaves from other trees into our data set and whatever else. But we'd have to we'd have to be checking in on the tree like daily to get our counts and whatever else. But that might not be a bad idea. Get like a square plot kind of marked out with rope or string or something, and then every day we check that plot every day. To see like how many leaves are there, or remove the leaves that have fallen and come back and check it every day. Yeah, it's good. All good ideas, right? So I think we have a really good grasp on quickly looking at an experiment that's being suggested and parsing out what the IV and DV are. You probably did this a lot in 7th and 8th grade. You should have anyway. All right. So we know already about hypotheses. But in case we forgot from like 5 slides ago, this is an explanation for a set of observations, right, that guides our experiment, right? And there's a lot of should's in there, right? Explanation for a set of observations which guide our further experimentation. All right, but make sure that you know that the hypothesis must be testable. It has to be testable. Right? If what you are suggesting as a connecting piece, or what you're suggesting as an explanation is not testable, then you probably are not in the realm of science and a study of the natural world, right? The existence of spookies. How are you going to test that? Well, we'll take pictures at night using like an IR camera. And if any dust particle or whatever floats in front of the camera and blurs it, if we kind of look at it squinting our eyes, it looks kind of like a face floating. That will confirm it. So we have to be able to test our hypothesis, right? It should also predict the relationship between the one independent variable that you have set up and the measurable dependent variable. Okay, so your hypothesis is, sometimes we talk about it as an if-then statement. Usually like the if component is referring to the independent variable, right? If plants do not require water, or in my denying plant water experiment, like I don't think plants need water. My plants in my yard seem to grow without me needing to water them. The dependent variable is going to be, the result. Then denying a plant water, it will still continue to grow as if I was watering it, or just as well, if not better, than the one that is being watered. So we should be able to predict that relationship using the hypothesis. All right, and then also the direction of that independent-dependent variable relationship should be included. Like, what is going to affect what? And it helps, again, to set that hypothesis statement up as an if-then statement, because it gives that directionality to the independent leading into the dependent variable. Okay, so this should be something that we are very familiar with. We should also keep in mind that when we design and develop and create hypotheses or hypotheses for our experiments, our investigations as we move through the year, that we make sure that's testable, predicts the relationship, and gives the direction of the IV and DV variables. The I and D variables. It's like saying rip in peace. Okay, so some example hypotheses in case you were wondering. Like, if the amount of fertilizer increases, the plants will grow. Is the if-then statement it's not, I don't think it's very specific. I don't know if we don't really specify a measurable part here. The plants will grow, like if grow more than the other, faster than the control, or whatever. So we could probably revise this a little bit, but we do have our independent variable. We're changing the amount of fertilizer. We're measuring the plant's growth. right? So we have a directionality to the setup of the hypothesis. All right, if the amount of fertilizer changes, the plant will change. Well, the plant will probably change regardless if we change the fertilizer or not. So again, not a very well written hypothesis. Right? Increasing the amount of fertilizer will cause an increase in plant height. Now that's getting pretty darn close to what we want, right? Because we're mentioning the independent variable that we're changing the amount of fertilizer, and we're going to measure the plant height. But you know, we might be able to add a little bit more detail into there in terms of, you know, will it increase in its plant height compared to the control? We might have a control plant set up that we're going to compare everything to. And then finally, if the amount of fertilizer increases, the plants will taste worse. Worse. I should have put worse, huh? Yeah, that's going to be rather subjective, isn't it? I mean, you grow carrots with and without fertilizer, and then maybe the person that you have taste test them, they don't like carrots, or maybe they like the fertilized carrots. I don't know. But so we have to be careful and be critical and really evaluate how we set up our hypotheses. All right. So those are some examples to kind of think about as we move forward. All right. So we do have some constants, right? So these are variables that do not change during the course of the experiment. Why do we do this? So that we know that the results are due to us and that independent variable that we have set up. Right? That the changes we see happen in our experiment can be tied to the independent variable, not any other factor. Right? Like maybe we're going to do the fertilizer with our plants. Right? We're going to see that if we apply fertilizer to a plant, it will grow more quickly. It'll gain height more quickly than a plant without fertilizer. But then we're also like moving the plants from window to window. When we come in, we take them off the windowsill, we water them, we put them back, but maybe not in the same spot. We're doing all other things that might affect our results. So that would be a part of these constants, part of these almost like controls of the experiment that we want to hold the same or keep the same throughout the entire duration of the experiment, because we don't want that to affect what we're doing. All right, so if the constants or things that we hold the same throughout the experiment, the same type of container, same type of like planting soil, the same type of same amount of water, same time they get watered, all that stuff falls under constants. A control or a control group is what we're going to compare everything else to. Right? It's like it's the plant that we just kind of do the typical thing with, and whatever that typical thing is, we also apply those typical things to the other test plants, except with what we're doing with the independent variable. Right? So it's the group that is chosen for that basis of comparison, the normal, the standard. I mean, I think we probably already know the why. The why is so we can know what effect your independent variable has on your experiment. Right? If all of our plants that we run have a different thing done to them, we can't. There's no normal to compare them to. There's not a control plant for us to go back to and say, well, this plant just got water and sunlight, and that's it. It's got just typical stuff. Now, if we have that control plant or control group in our data set, now we can compare whether if they got fertilizer, if it helped, if they got more or less water, how does that affect the plant? If they got more or less sunlight, how does that affect the plant? You need that control group or control set or reference data to compare things to. Sometimes this control information might just come from a text. It might say, typically, the North American dandelion grows at a rate of so many centimeters per day or whatever. So you might have some sort of normal data to reference to compare to. But oftentimes we end up just running our own control plant or growing our own controls. All right, are we okay to move ahead? Moving ahead. We should also consider the idea of repeated trials, because sometimes we need to repeat that process to make sure we kind of rule out error in the procedure that we conducted, right? And again, the reason, again, is to account for procedural error. Sometimes we use more than one subject, right? If we use more than one organism in an experiment, we can also account for the range of variability or variety from one organism to the next, right? Not every single rose bush is going to grow the same way, with the same number of branches in the same direction, with the same number of petals, the same number of leaves. I mean, they're going to be slightly different from one rose bush to the next, or from one pea plant to the next, or from one, I don't know, green onion to the next. But if we use many subjects in our test and run repeated trials, the data set that we get from that should be, one, low on error, and then also account for that range of variety that we have from one organism to the other, because each organism being slightly, being unique in many respects. Okay, we're on the downhill now. Going into data and data handling. Here we go. Whoops, already did that. All right, so data tables. Anytime you're going to then collect this information from your repeated trials, your multiple subjects, your experimental runs, right? Make sure your data table always has, because you'll lose points off your lab handout or lab report when you submit that. If you lack a title, right? We need to make sure that we have this title is going to describe what the table or the chart or the graph is showing us, right? It shouldn't just be like data table 1. It should be something that it kind of gives away what the data table is about. Average plant growth versus, amount of water, or average plant growth versus amount of sunlight, or whatever. That would be something that very easily points us in the direction of what this data is supposed to be showing us. Right? And then for our labels, we should make sure that we label the independent dependent variable. So that's gonna, we're gonna see some examples of some tables and graphs and charts. And especially in a data table, the independent variable needs to be kind of listed, like what are we doing to them, what is being altered, like maybe it's the amount of water, 0 milliliters, 10 milliliters per day, 20 milliliters per day. And then dependent variables, the measurement of growth on day 1, day 2, day 3, plant height from day 1, day 2, day 3. All right, so it's going to organize your data into columns and rows, really. So simple stuff. Also, make sure that we include, units and averages, because if all you put is like amount of water administered, 5 what? Cups, gallons, cubic feet, cubic meters. I mean, we don't know. Ham sandwiches. I mean, again, we don't know what you mean if you don't put a unit with the number or value. And then we should also, if we have numerical data to work with, and we have multiple trials or subjects, or maybe just data from the same subject, we're going to want to average that stuff. Okay? Because maybe we take several measurements. Maybe we measure plants 1 through 5 several times. Because we want to make sure, when we get our data set, that when I measure the height of that plant, if I measure plant 1, and then measure the other plants, and then come back to plant 1 and measure it again, those two measurements now that I have from the same plant should be pretty close, if not the same, but it kind of confirms that we're measuring them correctly and with the highest degree of precision that we can. Right, so we would want to average that and then plop that into our data table. Right, and then finally, probably one of the most important things is to make sure that you keep it organized and neat. because it's really difficult if you have a really messy, sloppy data table where the rows kind of slant up into the right and the columns like twist towards the bottom left of the page. It's hard to get lined up of what data belongs with what column. And so it's really, it really makes you work in a more efficient way if you keep things nice and neat. Now, with the use of the Chromebooks, that helps because you can use data tables on sheets and stuff to help you along. Insert a table into a Google Doc, all that stuff. But if you're handwriting some data down, try to be careful about it. Okay, the easy stuff. Data tables, right? Here's an example data table. Again, it's kind of hard for you to see the smaller text to the back of the room, but we'll quickly try to describe this. Right? So the hypothesis is that students who eat breakfast regularly will score higher on the ACT test. Right? The ACT test scores have no units, so we couldn't include those because there's points or value or score, a raw score value. Right? So we have has breakfast, male and female subjects, no breakfast, males and female subjects. Looks like we got lucky because we have 90 males and 90 females, 90 males and 90 females, so we have a total sample size of 360 people. 180 that did not have breakfast, and 180 of them that do have breakfast. And then we broke it down by grade level, right? And we find out that we took the average by gender of people in each of the grades. We have that information averaged out for counts of things. And at the very bottom, the overall average of their scores, of the resulting scores. Right. So overall, 22.8 versus 16 not breakfast. So I mean, from this information, it's evident that having breakfast before you go take that ACT or having breakfast on a regular basis helps improve your performance. So if you just get up, slap your clothes on, and roll into school without getting anything to eat, you're probably struggling a little bit. Right? Graphs. Remember that when we're working with graphs, that again, we're going to have that specific title. We're going to show that relationship between the IV and the DV, very much what we do with our hypotheses. And we make sure we label each axis. Why do we do that? Because it will help us identify the data and the results. Again, it's all about trying to let us know, like, what does the x-axis represent in those units? What does the y-axis represent in its units? All right, so we give it a title, a specific title, because we're showing the relationship between IV, DV, and then we're labeling axes so we know, like, what, helping the ID, the data, and the results. Right, when it comes to the units, again, we got to make sure that we include the units in either the labels that we post on our graph or chart, or maybe they get embedded, like maybe we actually show each data point and its value on the actual graph itself. Most people do not because they feel it clutters up the trend of the data. Most people would probably just have like a separate data table attached along with the graph that they create. And make sure that you choose the right type, right? A pie graph, a bar graph, histogram, or line graph or chart. It's going to depend on what you want to show. If you're comparing things out of a whole sample, then maybe a pie chart's the way to go. Right? If you're showing a trend over time, then a line graph. If you're trying to compare, again, categories, a bar graph might be appropriate. So you have to decide, like, what are you trying to show with this information? What do you want this quick glance at your data to look like and be reflective of? Because, let's be honest, a data table full of hundreds of rows and columns of numbers is not very telling. You have to really dig in. You have to know the experiment personally to understand what those numbers are telling you. But when you take those numbers and plop them into a graphic sort of way, or a graphic type of presentation, like a graph or a chart, it helps you at a glance understand what the data is telling you. Right? And then finally, we want to make sure that we have the right scale. So we don't want to use scale breaks. We don't want to say, like, on the y-axis, 0, 10, 20, squiggly line, 100, 150, you know, that's not going to be a very good presentation of the data, because it's going to shrink and squash and stretch your trend lines. Right? So you definitely don't want to do that. But you want to choose a scale where you can fit all of your data in one glance. And also make sure that your data points stay within those graph boundaries. We don't want data that trails off into no man's land when it comes to graphing. All right. In your note set, I believe that I have also included some of the images and examples of pie graph, bar graph, histograms, and line graphs. Just consider when they would be appropriate to use. We'll get into more detail as we move through some lab work in deciding what type of graph is best for what we're doing. For tomorrow, this assignment will post to Classroom middle of the day. But if you could check out Bozeman notes and check out the video on scientific method. Take notes in your science notebook for a stamp tomorrow, right? So Bozeman notes, scientific method, or the stamp in your chart tomorrow.
I have this because I'm going to give it back to me till last night.
That's fine, thank you. Thank you.